Hi everyone, today we're going to be discussing the next generation science standards. Last week you all built a concept map using the framework for K-12 science education practices, and those practices have evolved into the next generation science standards. If you're wondering why we're focusing on the next generation science standards, it's because these are the science standards that have been adopted nationwide by every state. So for example, you were working through the Louisiana state science standards, they are all adopted directly from the next generation science standards. So if you understand the next generation science standards, then you understand your state science standards as well. So what are the next generation science standards, or NGSS? Well, they're made up of three dimensions. You have practices, cross-cutting disciplines, and core ideas. And it rests on the view of science as both a body of knowledge and evidence-based model and theory building expertise or enterprise, So really what it's built on is your students doing. I mean, how many of us have actually enjoyed learning science just listening to someone talk about science? We like to do science. Next generation science standards continually extend, refine, and revise knowledge, and it prevents the three dimensions that will be combined to form each standard. So you have your core ideas, your practices, and your cross-cutting disciplines or ideas. And the combination of these dimensions is what brings us to our standards. So for example, I went over the standard, or a standard similar to this in a previous video, but you can see these three dimensions in the standards. So here you see the practice, you see the disciplinary core idea, and you see the cross-cutting concept. And we'll come back to this at the end of the presentation. So the first dimension is practice. So when we talk about practice, we're talking about skills. So it's going to describe the behaviors that scientists engage in as they investigate and build models and theories about the natural world. And the key set of engineering practices that engineers use as they design and build models and systems. So you'll always see science and engineering practices, or SEP, as one of the three dimensions of the next generation science standards. And you'll also see that in your Louisiana State Science Standard. See, science and engineering practices. And there's 7 different types of practices. So you'll notice that in the Louisiana State Standards, they only highlight in bold one of the practices that they want you to use in that standard. So you don't have to cover all 7 for each concept. You only have to cover the one that's bolded. So for example, in this particular state standard, 3-PS22, mobility and stability, forces and interactions, they want students to make observations and or measurements of an object's movement or motion, to provide evidence that a pattern can be used to predict future motion. And the science and engineering practice that they want you to use is planning and carrying out investigations. You'll see that the other 7 science and engineering practices are listed, but it's the one in bold that you need to attempt in your lesson for this particular concept. So we are going to go over the 7 different science and engineering practices in this lecture, as well as the cross-cutting concepts and a couple other things as well. So science and engineering practice 1 is asking questions for science and defining problems for engineering. And I've broken it down because we have teachers who are teaching all grades, but they have what's expected for K2 versus 3rd through 5th grade. So you'll see this table over and over again in this presentation. And that's because we need to consider the grade level that we're teaching, and the expectations might be a little different for our younger learners versus our older elementary learners. So in K2, asking questions and defining problems might be building on prior experiences and progresses to a simple descriptive question that can be tested. And I would highly recommend, in the phenomenon that you choose to showcase this, that it be something that your students have experienced, right? That could be a power outage, it could be a popsicle melting. It could be any number of things that a child could have experienced. And then you're going to ask questions based on observations to find more information about the natural and or designed world. Now, for our 3rd through 5th graders, you want them to be asking questions and defining problems that build on their K through 2 experiences. So you want to progress from what they've been practicing in kindergarten through 2nd grade. And one way you can do that is ask questions about what would happen if a variable changed. So you could use the exact same phenomenon that these students have talked about in kindergarten, 1st or 2nd grade, but now you can increase it. Like, what if the popsicle's bigger? What if it's a really cold day? What if it's a really hot day? What if you're eating your popsicle in the shade? Those could all be variables that you bring into the phenomenon. For K2, they want you to ask and or identify questions that can be answered by an investigation, and then define a simple problem that can be solved through the development of a new or improved object or tool. So coming back to the popsicle example, you could have your students ask and or identify questions that can be answered by an investigation. So naturally, your students are going to start to ask you things like, well, how hot is it outside? How fast did the child eat the popsicle? How did the child hold the popsicle? What kind of popsicle was it, right? Like, was it a cool pop, like that you push up through the plastic, or was it like a popsicle on a stick? So there can be a lot of questions with that. And then you could have your students come up with ideas on how to keep your popsicle frozen longer on a hot day. And I'm sure they will come up with some really great ideas. Now, for your 3rd through 5th graders, what's expected for the science and engineering practice is that your students start to identify testable and non-testable questions, and ask questions that can be investigated and predict reasonable outcomes. So we're starting to get them to think like within the scientific method. And then also have your students use prior knowledge to describe problems that can be solved. So maybe they can define a simple design problem that can be solved through the development of an object, tool, process, or system, and include several criteria for success and constraints on materials, time, or cost. So you're actually having them really consider and engineer a solution to a problem. Here's an example. This is a 3rd grade life science where they analyze and interpret data to provide evidence that plants and animals have traits inherited from parents. That variation of these traits exists in a group of similar organisms. And if you check out the Squarespace, which you have access to on your learning management system, Moodle, you can see a worksheet and you can kind of start to see an idea of how this science and engineering practice has been used. The second science and engineering practice is developing and using models. This is where you want students to construct models as helpful tools for representing ideas and explanations. These tools include diagrams, drawings, physical replicas, mathematical representations, analogies, and computer simulations. And I know that in a lot of our scripted curriculum, they provide you ways to either create or use already made models. Modeling tools are used to develop questions, predictions, and explanations. They can also be used to analyze and identify flaws in a system and communicate ideas. And models are used to build and revise scientific explanations and propose engineered systems. Measurements and observations are used to revise models and designs. I mean, how many of us, and this is literally on my desk right now, how many of us have done the solar system model? Here's your sun. Here is Venus, and Mars. How many of us have had students develop models in understanding just how far away the planets are in our solar systems and the size of how big they are? So that's a very simple way to include models in your lesson. So in K2, we want the models to build on prior experiences. And most of the models in K2 are going to be drawings or physical replica or diorama, or maybe even a storyboard. You want your students to be able to distinguish between a model and the actual object and compare a model to identify common features and differences. You might be able to develop and use a model to represent amounts, relationships, or relative scale, so bigger versus smaller, and develop a simple model based on evidence to represent a proposed object or tool. Now, once you get to the older grades, we want you to progress on that. So you want your students to be able to identify things like the limitations of a model. You also want your students to learn how to work together to develop and revise models. And they could be using abstract representation to describe a scientific principle or design a solution. And you also want your students to be able to develop a diagram or simple physical prototype to convey a proposed object, tool, or process. And then use a model to test cause and effect relationships or interactions concerning the function of a natural or design system. So in that sense, you might have your students understanding like, well, let's change a variable and tell me how your model will respond to that variable. The third science and engineering practice is planning and carrying out investigations. I mean, for me, this is the most fun practice. This is when students should have the opportunity to not only carry out several different kinds of investigations in their elementary education, but also start having the opportunity to plan. Now, in this science and engineering practice, there is a lot of scaffolding that needs to happen, but there's so many opportunities within a scientific unit for your students by the end of that unit to be literally planning out and executing that investigation. At all levels, they should engage in investigation that range from those structured by the teacher. So for example, maybe you do a demonstration or you literally have them follow an investigation step by step. And until you get to the point where the student can decide how many times they're going to test something, how they're going to test something, what are their variables, what are their constants, and what is their hypothesis. So here's a great diagram of how to plan out an investigation. And, you know, there's things like your students need to think about their hypothesis. They need to think about the equipment they're going to use, what method they're going to use, what is going to be their step by step of their investigation. You want to know exactly what they're going to do. And then they also have to record the results, right? You have to provide a way for them to record their actual data so that they can make conclusions from that investigation. Here are the differences between K2 and 3 through 5. As you can imagine, K through 2 is going to be a lot of probably group work where they're going to be planning an investigation as a class, versus in 3rd through 5th, you would have individuals or small groups doing it. And I'll let you look over this table. Here's a great example of an investigation with apple browning. This teacher does an excellent job of explaining how she runs the investigation and how she allows the students to plan the investigation themselves. And she's doing it with very young children. I think they must be in kindergarten or pre-K. So definitely check this out because it's a really nice video that models how to execute this particular practice. This practice makes a lot of my teachers nervous, and that's analyzing and interpreting data. I think when we hear that, we think like, well, how can a kindergarten through 2nd grader know how to interpret data? But you can collect data and present it in all sorts of different forms that can reveal patterns and relationships and allows results to be communicated to each other. This could be as simple as taking the heights of all the students in your class, doing fingerprinting and identifying the different types of fingerprints that each classmate has. You could do hair color, eye color. There's so many different data points that you can take to show them how data is represented. If you are teaching Eureka Math and you're also teaching science, there's a lot of ways in which you can bring in mean, median, all those graphing, all those different concepts that you're already teaching in math into your science lesson as well. Because raw data has such little meaning, a major practice is scientists have to organize and interpret data using tables, graphing, and statistical analysis. And so you see this a lot in secondary, but you can definitely introduce it in your elementary classes. And this really gives meaning to the data, and then you can connect it back to the phenomenon. So you're probably wondering, like, what can a kindergarten through second grader do with analyzing and interpreting data? And you can see that there's actually holes in the table, right? Because they are lacking math skills at that point. But they can use information from observations to construct an account of a natural phenomenon. So you might have them look at a picture or watch a video and then explain what's happening. And you can use tools and or materials to design and or build a device that solves a specific problem and then compare the solutions. For your third through fifth students, you would actually have your students use evidence such as measurements, observations, or patterns to construct or support an explanation or design a solution to a problem. I love using analyzing, interpreting data, engineering, science and engineering practice for lessons about weather, seasons, moon cycles, because you can easily see where students can make observations and identify patterns. And then you can have them apply scientific ideas ideas to solve design problems. So, like I said, I love doing this with weather. Also, the Science and Engineering Practice 5 is using mathematics and computational thinking. Again, I provide a weather lesson for you. Please check it out on our learning management system. But students are expected to use mathematics to represent physical variables and their relationships to make quantitative predictions. I really love doing this with, there's a great third grade standard on weather, and it talks about making predictions. And so what you can do is you can get last year's weather data and have them find the average temperature for the week that you're teaching this. And you can ask them, well, based on last year's weather, do you think it's going to be similar to this week's? And then you can talk about it, and then you can have them collect data that week and compare how different the weather was. And then you can talk about like when there's record highs and record lows and hurricanes and things like that change the weather drastically. So I'm a big proponent of using weather for this particular science and engineering practice. In K2, what you want to do is decide when to use qualitative versus quantitative data. And this is a terrific lesson for students to use. You know how like we always ask our students to like predict the number of beans or jelly beans in a jar. That is a great place where you can talk about qualitative versus quantitative data. You can use counting and numbers to identify and describe patterns in the natural and designed world. You would be amazed at how many patterns you can find in nature, if it's the colors of flowers or the way petals and leaves are designed, but you will find patterns throughout the natural world. For your third through fifth graders, they need to be able to organize simple data sets and reveal patterns that suggest a relationship. And they need to be able to describe, measure, estimate, and or graph quantities such as area, volume, weight, and time to address scientific and engineering questions and problems. We're almost there, folks, I promise. You also want your students to be able to construct explanations and design solutions. And this is going to feel really ambitious for some of us, but there's a lot of ways that you can do this. So you can ask students to demonstrate their own understanding of the implications of a scientific idea by developing their own explanations or phenomenon, whether based on observations they've made or models they've developed. So you can have them describe a phenomenon and explain it, or you could give them a phenomenon and have them describe it and then design a solution for it. And I highly recommend that you watch this Bozeman video on this. He gives some really great examples of this. So here's one that I really love, and it's building the ring using Pringle chips. And so you're probably like, really? That could have been one of them, but I have a whole lesson plan for that, so you can go check that out if it meets a Louisiana science standard that you're teaching. But here, what you want to focus on with K2 is that your students use information from observations to construct an evidence-based account of the natural phenomenon. So maybe they watch something or they read a book about a natural phenomenon, and then they have to use that information to construct evidence-based account of it. For your 3rd through 5th graders, they need to be able to identify the evidence that supports particular points in an explanation. And I know that some of you who teach lit are probably thinking, don't we already do that in our literature classes? And you do. So you can actually apply some of the concepts that you're teaching in other subjects to this particular type of lesson. And then last but not least, I think there's only 7, I could be wrong. We need to engage, so you might see this, and this is probably towards the end of the sequence and scope of the Louisiana Science Standards, but the Science and Engineering Practice 7, which is engaging in argument from evidence. Oh, there's 8 actually. Argumentation is a process for reaching agreement about explanation and design solutions. In science, reasoning and argument based on evidence are essential in identifying the best explanation for a natural phenomenon. And in engineering, reasoning and argument are needed to identify the best solution to design a problem. So this is where your students are going to have to be able to defend their reasoning or their design, depending on what you're teaching. So here's an example. Young students can begin by constructing an argument of their own interpretation of the phenomenon they observe and any data they collect. And then they need instructional support to go beyond simply making claims. And there's a whole bunch of things you can use in the argumentation toolkit, so definitely check that out in this lecture. So you can check that out as well. And here's a really great one that kind of tells you how to do this. But you can see here's the evidence card sort, and you can see claim A versus claim B. And then they have an oral discussion about it, and then they can discuss together which they agree upon. And you can see they're gathering evidence, etc. And then the last one is the Science Engineering Practice 8, obtaining, evaluating, and communicating information. I personally think right now, as we are in our 4th wave of the COVID pandemic, that students being able to read, interpret, and produce scientific and technical texts are really important, but most importantly is being a critical consumer of information about science. I think the biggest thing that you can do as a science teacher is have your students be able to go on social media or go on the internet and identify what is real and what is fake. And so really think about how you're going to do that and how you're going to teach your students how to be critical consumers of information when it comes to science. And there's actually some really great tips for both K2 and 3rd through 5th. So reading appropriate texts, again, that can bleed into your ELA lessons, and describing specific images that support an idea, obtain information using various texts. So you might have to provide the text to your kindergartners, but they could see what supports this idea or negates it, and then having them communicate that idea. In 3rd through 5th, again, you would read grade appropriate texts, and you could compare or combine across complex texts and other reliable media to support the engagement in other scientific and engineering practices. So you could also use YouTube videos, newspaper articles, and other things that your students might be able to read and watch. So those were all the science and engineering practices. The other dimensions of the next generation science standards are cross-cutting concepts. Cross-cutting concepts have applications across all domains of science. As such, they are a way of linking the different domains of science. They include patterns, similarity and diversity, cause and effect, scale, proportion and quantity, systems and system models, energy and matter, structure and function, and stability and change. And then we also have our DCI. This is are discipline specific. So we have 4 domains. You have life science, physical science, earth and space, and engineering, technology, application, and science. And these disciplinary core ideas, they have the power to focus K through 12 science curriculum instruction and assessment on the most important aspects of science. So they provide a key tool for understanding or investigating more complex ideas. They relate to the interests and life experiences of your students, and they may be teachable and learnable over multiple grades. So that would be an example of using a phenomenon that your students revisit a few times over their elementary education. This is a fantastic video for you to watch. It's basically a summary of exactly what is the Next Generation Science Standards. It's also posted in your learning management system from the previous week. And let's go back to that Louisiana Science Standard. So this is 3-PS2-2, motion and stability, forces and interaction. It is expected that the teacher that is teaching this lesson is going to have their students make observations and or measurements of an object's motion to provide evidence that a pattern can be used to predict future motion. Now, if you're reading that and you're going, what? Huh? Then go for the clarification statement. Examples of motion with a predictable pattern could include a child swinging in a swing, a ball rolling back and forth in a ball, or two children on a seesaw. And so what needs to be met in this Next Generation Science Standard, which has also been adopted by Louisiana, is that you have your students using the science and engineering practice of planning and carrying out an investigation. So you will have your students actually plan out and carry out an investigation around a phenomenon. And then the disciplinary core idea that needs to be met, the DCI that needs to be met in this lesson, is that patterns of an object's motion in various situations can be observed and measured. And when the past motion exhibits a regular pattern, future motion can be predicted from it. And there's technical terms such as magnitude, velocity, momentum, vector quantity. They may not be introduced at this level, but they should be able to start describing those types of things. And then the cross-cutting concept is patterns of change can be used to make predictions. So for this week's assignment, you are going to pick a Louisiana state standard that I have not discussed, and you're going to break down that Louisiana standard. You're going to explain the I can statement you would have your students use. You're going to explain to me what that actually means, and then you are going to describe in your own words what are the three dimensions, so the SCP, the DCI, and the CCC, or the science and engineering practice, the cross-cutting concept, and your discipline core information. So please explain everything in your own words and what this means. Thanks so much, and have a great week.